Hello everyone. So we have discussed about plastic wave of uniaxial stress and plastic wave of combined stress, that is shear and longitudinal plastic wave. So we have seen different experiments to produce plastic shear wave with plastic longitudinal wave. So now in this lecture we will discuss about the Taylor's experiment, which is also known as bar impact experiment, bar of finite length, and this is a classic experiment to test the dynamic constitutive behavior of materials. So Taylor in 1948 he developed first this experiment during the World War II. 1948, Taylor's experiment. So Taylor described the test in a sequence of events, that is elastic and plastic wave propagation. Before going to details about that, we will try to understand the difference between quasi-static deformation and dynamic impact. So suppose we have a quasi-static compression here. This is a cylindrical bar which is compressed. Let's say this bar is compressed the top side. So after compression, what will happen is the cross sectional area, will be constant at any time, then neglecting the friction at the ends. So what will happen is the cross section will be uniform throughout the length. It got compressed, but cross section area will be uniform throughout the length during the test and at any given time t, and we neglect the friction at the end, at these ends, and neglecting friction at ends. So now for dynamic impact, let's assume that there is rigid wall and the cylindrical bar is impacting on this rigid wall. So after the impact, so the bar will take a shape like this. This is after impact. So the shape of the object during the deformation and after the deformation, they are not uniform. The part of the cylinder which is close to the impact, that is which the part of the cylinder that is undergoing the impact with the rigid wall, so this will be highly deformed. So if you see that this part will be highly deformed, and other part the deformation will be less, it is highly deformed. So the Taylor described the test as a sequence of elastic and plastic wave propagation. So you will see the sequence here. Suppose this is the rigid wall and this is first case is the prior to impact. So let's assume this is case number 1, 2, 3, 4, 5 and 6. So these are the sequences. So prior to impact, this is u is the impact velocity. You can see this is not touching now. So impact velocity is u, impact velocity u. The length of the bar is L. So if you see that the length is decreasing here, so after the impact, this is upon the impact, the length is decreasing. It is decreasing gradually. If you see the step 2, 3, 4, 5, 6, it is decreasing gradually. So this part is the plastically deformed part. Deformed part. If you see, the stress wave will start from the wall surface, and this is the elastic wave velocity c, which will be ahead of the plastic wave. The plastic wave velocity we are writing as small v. So and this, let's say this portion is h, which is the length of the small h, which is the length of the plastically deformed part. So here we have u. So this is actually u is the same as the particle velocity here. We will discuss about that later. This elastic wave is elastic. This is a compressional wave. And even the plastic wave is following that the elastic wave. So at the third step, so what will happen is this plastically deformed zone will be now longer. So you can see that plastically deformed zone is now thickness is more, and then as we told earlier, this is the elastic wave velocity wave front, this one, and this is the plastic wave front, and this is u. So now at this position, at step number 4, so what is happening here is the elastic wave hits the free surface here, this free surface, back surface, and it's going back now. Though it is going back now, elastic wave. This is we call a release wave, that is reflected back, and here the plastic wave is still advancing, and at some point what happened is this reflected elastic wave will meet the plastic wave, and then at that point that means we will call release wave, the reflected wave, elastic wave. The release wave will meet, the release wave will meet the plastic wave. At that point the stress will become 0, and that is the end of deformation. This is basically interaction of the release wave with the plastic wave. So a release wave is the reflected elastic wave back from the back surface, this back surface. It is so basically this is the interaction. I will write here interaction of release wave and plastic will lead to reduce the stress to 0, and that is the end of the deformation. Now as you can see, this Now the length of the bar is slowly reducing from 1 to step 6, and if we see in the details in this diagram, so we can see that the plastic wave front, first one is the plastic wave front, and this one is, the second one is elastic wave front. Okay. So this plastic wave front, you can see that this is the plastically deformed area, this area is the plastically deformed area. The plastically deformed area, that plastic wave front is traveling at a velocity small v, and we know that this is the area A, the cross sectional area, and this, the area is A naught in this portion. This is the area, not the length. We are writing this way. So area A naught, which is the smaller than the area A is in the plastically deformed part. So as you know, this impact velocity was u, and we will say that this is the interface I, that is the interface between the plastically deformed part and the other part. Similarly, for elastic wave, we know that when the elastic wave will go through this area, let us say this area. So we are showing it in a the second diagram. Let us say the first diagram is diagram A and the second one is diagram B. So here what is happening is the elastic wave front with a velocity c, it is advancing towards the left, and this is, let us say, the particle velocity up, and we can say that the density is different here. This is rho and this is rho naught. So it is the initial density and rho naught and rho, because the compressive elastic wave is changing the density. But in the other case, in the diagram A, we have the rho on both the side of the interface are same. So this rho and this rho, they are the same, they are both equal. But in the elastic wave case, we are assuming that the compressive elastic wave will reduce the density. So basically on the right hand side, the rho naught is the initial mass density, and the right hand side, because of the compressive wave travels through that part, and that is why it compressed the material, making the actual density higher. So now we will try to derive some relations between strain and stress and impact velocity. So we will see how to go forward. So in the first case, in the diagram number, this is diagram A, so we can have conservation of mass, So the virgin material, that means the material on the left side of the interface. So this material that moves into the interface. So this material moves into the interface with a velocity u plus v. So that means I will tell you, this is mass in will be equal to mass out for a conservation of mass. This velocity, so with which this the thicker line, So the small v1 is the for plastic wavefront, but the mass, the virgin material will enter into the plastically deformed part, that means the towards the right side of the interface, and the velocity will be capital U plus small v, because as you know this impact velocity is u and the interface is coming towards left side with a velocity v, that is the plastic wave front velocity. Or what we can do is we can write the v somewhere here to make it even clearer. So now this part of the material on the left side of the interface will enter inside the interface, that is towards the right side, with a velocity u plus v, because u is the velocity of the impact and v is the velocity at which the interface is coming towards the left side. So that means the relative velocity. So we have u plus small v and multiplied by your area A naught, and we have rho. So this is mass, rho into area into that velocity, the mass in, and which will be equal to, on the right hand side area will be A, rho is same, and then the small v, because the material that is on the right hand side, that is going away from the interface at a speed of v, because at a speed of small v the interface is going towards the left side, that means the material on the right side is going at a speed of small v towards the right side, it is going away from the interface. So, so this is the conservation of mass equation. So as we know, both the density are same in this case, and so basically we'll end up with A naught u plus small v A small v. So after that we will use the conservation of momentum, which is that which means that the change in momentum is equals the impulse, change in momentum is equal the impulse. So I have noticed that these lines were not shown earlier, so you can draw these lines. So now it will be more clear to you. Somehow due to some technical problem, these lines were not shown and these arrows. So we are discussing about the conservation of momentum. So we have the bar with the plastic deformation, that means bar impacted on a rigid wall, and this part is the plastically deformed part. And let's assume that as we know, anyways, we have this area A here and area A naught here, and let's assume that the material is, and we have the interface here, let's assume that the material is entering from left side to the right side, material flow. So this small length dl is the material going entering into the plastically deformed area. So dl will be equal to, as we discussed, this is u plus small v, that is the velocity in the relative velocity of the material going inside the interface. Inside means from left to right of the interface, and let's assume that the time taken is dt. So, time taken is dt, and also the mass of this small element is, let us say, rho a naught dl. So, this is equal to rho a naught u plus small v dt. So, dl we found as u plus v. So, yeah, let us assume that this is the interface. This is the interface. So, now from the Newton's second law, so we have force equal to acceleration into the mass. So, force here is a minus a naught into the stress, and that means sigma yd is nothing but the dynamic yield stress. So, in the plastically deformed zone, so the stress within that region is constant, and that is sigma yd, because the plastically deformed zone stress doesn't exceed that stress limit. So, there is dynamic yield stress, it is not static yield stress. So, yield stress at the highest strain rate, yield stress at that strain rate, and that is why so across the interface, that is across the interface I, so this force will be a minus a naught into sigma yd, which is compressive. So, this is equal to minus sign. So, this is the force which is equal to minus of a minus a naught sigma yd, that will be equal to acceleration into mass. So, acceleration will write gamma, and the mass is dm. Gamma is the acceleration of that element. So, now we have this acceleration, gamma is equal to, so basically the material is going inside this plastically deformed part, and the initial velocity is u and the final velocity is 0, that happens in time dt. So, this will be equal to u dt. Now, if you have this as gamma u dt and dm from the above expression, rho a naught capital U small v dt, and on the left hand side is minus a naught sigma yd. So, that will give us, we can, so dt will get cancelled, and we can write this by rearranging u plus small v capital U, the same capital U is equal to sigma yd a minus a naught. So, basically this is the conservation of momentum, sorry, this should be conservation of momentum, not motion. So, now we have two relations with us. One is the conservation of mass. Initially we got that expression, and then another relation is from conservation of momentum. So we will combine these two to get a final expression. So what we will do is, from conservation of mass, we found that we will try to eliminate the small v from this to a minus a naught small v plus a naught u is equal to 0, and if we have the small v, that will be equal to a naught u, capital U, a minus a naught. From the conservation of momentum, from this is conservation of mass, from conservation of momentum, what we can get is rho a naught small v u plus rho a naught u square equal to sigma y d a minus a naught. So if we substitute this v with this, so we will find rho a naught u a minus a naught u plus rho a naught u square is equal to sigma y d a minus a naught. And then little simplifying, a naught square u square a minus a naught plus rho a naught u square sigma y d a minus a naught. We will try to simplify it more, taking that term common, a naught square a minus a naught plus a naught a minus a naught. So we will take the term common, and then we will again find this term in terms of a and a naught. So how it will look like is, okay, we will keep it here itself on the left hand side, a minus a naught square plus a naught minus a naught square, okay, is equal to a minus a naught. So further rearranging, sigma y d equal to a square plus a naught square minus twice a naught a naught. So what we will do is, we know that the volume is constant to get the expression in terms of strain. So what we do is that we know the volume is constrained during plastic deformation, so we assume it actually like that. So I assume for plastic deformation, which is not the case in elastic deformation. Plastic deformation, we can assume it as constant, that is equal to strain is equal to L naught minus L. We know this length of the bar, initial length and the final length, divided by L naught, which will be given as V naught A naught minus V naught A, because volume is constant, divided by V naught A naught, and that will give us 1 minus A naught by A is the strain. So now in the earlier expression, this expression, what we can do now is on the top. So what we can do is we can divide both numerator and denominator by A square, and then we will see if we can reduce that to an expression of strain. So this above expression will give us will give us 1 plus A naught A, this is square minus twice A naught A divided by A naught by A, which will be equal to, and the above it is actually from this we can write it epsilon square, and the below it is 1 minus epsilon. So now we have arrived at the final expression. So we have an expression of the mass density with the impact velocity with a dynamic yield stress, which will be equal to as a function of strain. So epsilon divided by 1 minus epsilon. Sorry, so we left the square here, that should be epsilon square. Okay, so now we will talk about the elastic region. So elastic part, already we have seen that as we discussed in the figure B, in the bottom figure. So we have the elastic wave velocity C and particle velocity UP, and the densities are different. So we can even draw that here. We can draw it here again. So the elastic wave front, which is moving from right to left, it is C is the elastic wave velocity, and the particle velocity is we are referring as UP. So now initially the mass density is rho naught, but when the wave travels from right to left, so the right side of the this wave front, where the wave already the compressed elastic wave already passed through, that the density will be little higher. This is the rho, the other one is rho naught. Now we are talking about this elastic region, so we will talk about the particle velocity in the elastic region. Particle velocity. So conservation of mass here, in this case you can see that the area is constant, let us say it is only A. So then the density are different. So what will happen is mass in, okay, we will write it like this. So conservation of mass in is equal to mass out. So mass going from the left side of this interface to right is rho naught c, because the interface is moving towards left at a velocity c, and then mass out is, that is the velocity density rho multiplied by c minus up, that is the relative velocity, because c is the velocity that interface is moving towards left from the right side, and up is also the velocity of the particles or material towards the left side. So we will end up with this expression for conservation of mass for the elastic front. So for this elastic wave front, which you can see here, elastic wave front. Okay, so from here actually we can get the particle velocity in terms of density and wave velocity, which will be rho minus rho naught divided by rho into c, that elastic longitudinal wave velocity. So this is equal to, we will see what is the relation of this with the strain. So strain, so now we will try to have the strain expression and relate with this particle velocity. So the strain, we write it as epsilon 2, which is because the earlier we wrote epsilon 1, and this is in the for the plastic wavefront we are trying to get the expression. So we are, that's why we are writing as epsilon 2, and that will be equal to L naught minus L divided by L naught, that is the length of the bar. So and this will be equal to V naught minus V divided by V naught, that is the volume actually, not any velocity, this is volume, and we know that the volume is not constant, as we have seen that we already discussed that the density will be different and volume will be different. So this will give us actually rho minus rho naught as rho, because area is constant. So area is constant. If we are wondering how we get this from volume to density, so it's like if you start from here, rho minus rho naught, this will be your mass into V minus your mass, the same mass by V naught, and divided by there is m by V, so which will be equal to V naught minus V divided by V naught. Yes, that will be will lead to this if we do that. So this is not needed. So just to tell you that if it is V naught minus V, that will be it will be opposite rho by rho minus rho naught divided by rho. So now we understood that the earlier expression what we got is rho minus rho naught divided by rho, which is actually related to strain, so that is epsilon 2. So then what we can get, that up is equal to epsilon 2 into c, epsilon 2 into c, and the material is elastic. We can use Hooke's law. We are talking about elastic wave propagation, so we can use Hooke's law, which will give you epsilon, we will write epsilon 2 here, so epsilon sigma by E, that is the Young's modulus. So that is from here now you can write up is equal to sigma by E. So sigma by E and C. So again we know that the elastic wave velocity c is equal to Young's square root of the ratio of Young's modulus by density, which is rho naught, the initial density in this case, and that's why or we can write even E as rho naught c square. So in this case, So if we write rho naught c square here and then sigma c, so up will be sigma rho naught c. So this is the particle velocity due to the elastic wave. So particle velocity for an elastic wave. But if you consider the impact velocity u, then the particle velocity will be different, and then particle velocity we can find out the particle velocity for 3 different regions in the, if we say see the sequence of steps earlier. Suppose the first step is, so what will happen when this is region number 1, let's say this is region 1, or don't be confused with the other numbers 1 2 3 4. So this is region 1, or better I would write R1, region 1 here, region 1, this R1. This case is when the elastic wave is has not crossed that region yet, and this is the region number 1, and then region number 2 is somewhere here, R2, that is inside the elastic wave region. That means that's on the right hand side of the elastic wave front. And then third region is let's assume that after the release wave reflects back from the back surface. So this is R3, sorry, let's assume this is R3, region 3. So this is, that is in the towards the back surface. This is the region near the back surface when the elastic wave is already reflected back from the back surface. So now these 3 regions, if we see the particle velocity in the region 1, R1, the particle velocity is nothing but the impact velocity, because the wave elastic wave has not reached that part, and only the impact velocity will be the particle velocity here. And for region 2, what happens for the region 2? So the particle velocity up will be equal to u minus sigma dynamic yield strength, divided by c rho naught, whatever that expression we have just now derived. So that is the expression of particle velocity due to the elastic wave propagation. But in this case, because not only the elastic wave propagation, this term, but also the impact velocity will have a role. So that's why this will be the resultant will be u minus sigma, this is actually subscript yd, this is sigma subscript yd, this. And in the region 3, so what will happen is when the particle at the free surface will have actually twice the velocity that we have derived for elastic wave profile. That means because that wave reflects back from the back surface, that's why for the particle velocity for the elastic wave, that will be twice of sigma yd divided by c rho naught. So this is the particle velocity due to the elastic wave, and that is because of the wave comes towards left and reflects back from the surface, and that's why this will be twice of that. And with that, this the impact velocity will also will be there. The resultant will be the particle velocity is equal to the impact velocity u minus this u actually minus sigma yd by c rho naught. So sorry this. So there are, what we learned here is, so we have the region 1 and region 2 and the region 3 here. So we have different particle velocity. So in the region 1 it is only the impact velocity of the bar, and region 2 and 3 we have both the impact velocity and the particle velocity contribution from the elastic wave is working contributing to it. Sorry, some of the lines here in the earlier slides, especially the arrows were not shown properly. That is probably some technical difficulty with the machine. So I am inserting the slide again. So I have noticed that especially these arrows were not shown in that earlier in the recording. So I had to insert it again to show these arrows. So yeah, I hope that will clarify your confusion. I think sorry about that, that is due to some technical difficulty of the machine. So that's all for this lecture. So we will continue this discussion, that is the Taylor's experiment, which is a actually the experiment for the constitutive behavior of material at high strain rate, and that is nothing but the impact of bars of finite length. So we will continue this discussion to the next lecture. Thank you.